We can use a two-way table to help us find probabilities. Here on your screen we have results from a 2012 General Social Survey which asked people about their happiness and whether they agreed with the following statement. In a marriage, the husband should work and the wife should take care of the home. The table here summarizes the data collected. So notice an entry here tells you how many people were categorized as happy and answered don't know to the question. The bottom row and the last column give you the totals across the rows and the columns. You should be able to compute those based on the data inside the table if you were not given that total in your original table. Let's try computing some probabilities. Suppose a person is randomly selected from the group. What's the probability that we select someone who is happy and agrees? Well, if we look at the table, the people that responded that they were happy and agreed with the statement are in this box here that comes from the happy row and the agree column. So the number of happy and agree, let's start with that, is 242. Now remember, my probability is the number in my event divided by the number in my sample. Now here my sample is the total number of people interviewed, and in this case that's going to be the total found here in the bottom right corner of our table. So the total in my sample space was 1146. If I plug this into my calculator, 242 divided by 1146, I get 0.211. So I have a probability of 0.211. What's the probability that the person chosen is happy or agrees? Now this is a little trickier. So I want to know how many people are happy or agree. Well, I know here, if I scroll to the right, that the total number of people that were happy was 991. And if I scroll to the bottom, the total number of people that agreed was 287. So how many are happy or agree? Well, I could add these two numbers together. Let's do this below. Happy or agree. 991 plus 287. But notice those two numbers came from adding the three numbers in the first row. That's how I got the 991. And we got the 287 by adding the two numbers in the first column. Now when I do that, I've counted this 242 twice. Do you see that? So that 242 people have been counted twice here. So I need to subtract it once. So I'm going to subtract 242 here. Now if I add those and subtract, I get 1,036. Now you could also get this number by reading in the table and just adding, let me highlight in green, adding each of these green numbers. So if I were to add those numbers up, let's do that over here. 242 plus 65 plus 684 plus 45. I get 1,036. That's the same number that I got below here. So you can find that number either way. Either way, that's the number that are happy or agree. So my probability is the number in my event divided by the number in my sample space. In this case, I get 1,036 divided by 1146. I get 0.904. How about the probability that we choose someone who agrees or doesn't know? Let me erase some of this marking on our table. So now if I want to know agrees or don't know, well, here's the agree column. Let me use the highlighter. And here's my don't know. Now here there's no overlap. So if I want to know the number that are either in agree or don't know, I can just add 287, the number that agree, plus 95. So I want the number that agree or don't know divided by the number in my sample. Here I'm going to take 287 plus 95 divided by 1146. That's 382 divided by 1146. Or 0.3 repeating. So what we saw on the last slide actually is a rule when we're dealing with probabilities of ors. Okay, so the probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. And in fact, we saw when we counted that the number of things in A or B is equal to the number of things in A plus the number of things in B minus the number of things in A and B. And we just subtract that because it was double counted in both A and in B's count. Okay? So again, be careful about double counting. On the bottom you have a picture representation. So if A is the blue circle and B is the yellow circle, the green overlap is what's in A and B. And so you can see if we were to count the people in A and then count the people in B, we would have counted the people in the green overlap twice. And so that's why we subtract that off. So let's look at this again. If we wanted to find the probability of being happy or agree, we could find the probability of being happy. So let's apply our rule here off to the side. Let's use a smiley face. Happy or agree is the probability of being happy plus the probability of agreeing minus the probability of being happy and agreeing. Okay. The probability of happy, I'm going to look at my happy row and find the total number of happy, 991, and divide by the total in my sample. And then I want to add the probability of agreeing. Agree is this first column. The number that agreed was 287. So 287 over 1146 is the probability that someone agrees. And then I need to subtract the probability that someone is happy and agrees. To be happy and agree, you're in the square that corresponds to both the happy row and the agree column. That's 242 over 1146. Now if you plug this into your calculator, you get 1036 divided by 1146, or 0.904, which is what we got on the previous slide. Two events are called mutually exclusive if they share no outcomes in common. So if you remember, our last example a couple slides ago was the probability that someone agrees or doesn't know. Those two events were mutually exclusive. If I wanted to know that someone agrees and doesn't know, then that probability is 0 because there's no one that lives in both agree and don't know. So if two events are mutually exclusive, then they cannot happen at the same time. So the probability of A and B is going to be 0. That means if I plug into the OR rule, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. But in the event that A and B are mutually exclusive, this last term is 0. So we get probability of A or B equals probability of A plus probability of B. This is only for mutually exclusive events. So you have to check if you want to drop the subtraction there. Here's the example that we saw before. What's the probability that someone agrees or doesn't know? Well, since those two events are mutually exclusive, I can just add the probabilities that someone agrees plus the probability someone doesn't know. The probability of agreeing was 287 over 1146, and the probability that you don't know is 95 over 1146. And if I add those together and divide by 1146, I get 0.3 repeating, which is what we got before. The events happy and agree are not mutually exclusive events because there's a group of people who appear in both categories at the same time. The picture you might want to have in your mind again is here's my happy set of people, and here's my agree set of people, not drawn to scale. So there were 991 total people in my happy group, but in the middle there are 242 people that live both in the happy and the agree circles. Let's look at some examples. Let's suppose we roll a fair-sided 6-sided die and record the face up. Let's find some probabilities. What's the probability that you roll an odd number or a number greater than 3? Well, let's let A be the event we get an odd number, and B be the event we get a number greater than 3. What is in A and B? Well, the odd numbers are 1, 3, and 5. The numbers greater than 3 are 4, 5, and 6. What is in A or B? Well, to be in A or B, you have to be in A or in B or in both. So that's going to include 1, 3, and 5 because they live in A, but also 4 and 6 because they live in B. I didn't write 5 again because we already have 5 listed. Finally, what's the probability of A or B? Well, that's the number of things in A or B divided by the number of things in my sample space. In this case, there are 5 things in A or B and 6 things in my sample space. Remember, my possible outcomes are 1, 2, 3, 4, 5, and 6. What's the probability that I roll a number less than 3 or roll a 6? So here let's use C and D for my events. Let's let C be a number less than 3. What lives in C? I could roll a 1 or a 2. What are the outcomes in D? Well, D is rolling a 6. Are these two events mutually exclusive? Well, these two events have no outcomes in common, so we would say that they are mutually exclusive. So the probability of C or D occurring is equal to the probability of C plus the probability of D, which in this case the probability of C is the number of things in C, which is 2, divided by the number of things in my sample space, 6, plus the probability of D is the number of things in D, divided by the number of things in my sample space. So I get 3/6 or 1/2.